In this screencast, we explore the relationship between the average rate of change and the slope. So we start by giving the definition of the slope of a line. So given 2 points, suppose you are given 2 points in the plane, x1, y1 and x2, y2. The slope of the line or line segment that connects these points, we're going to call that m. The slope of that line is delta y over delta x. Delta y represents the change in the y coordinates, and delta x represents the change in the x coordinates. So y2 minus y1 would be the total change in y, and x2 minus x1 would be the total change in x. The graph below illustrates the definition of slope. So here we are, we have 2 points, and we connect these 2 points with a line. The coordinates of this point are x1, y1, so that would mean right about here is x1, and right about here is y1. And the coordinates of this point are x2, y2, so that would mean right about here is x2, and right about here is y2. So what we're after when we talk about slope is we're trying to measure how steep a line is. And the way we do this is we look at how much a line rises or falls relative to how far left and right it moves over the same period. So how do we quantify this? Well, this distance from here to here is simply the total change in x between x1 and x2. So the total change in x is found by taking x2 minus x1. So that's what we're talking about right here. And in terms of how far the graph rises, we calculate that by looking at the change in the y values, the total change in the y values. The total change in the y values would be this distance right here. So that's the delta y. And you can see we've got delta y represented over here. So this distance right here is exactly the same as this distance right here. So the change in y gives you this distance. The change in x gives you this distance. And the slope, or the steepness of the line, is what we call m. That is the ratio of these two distances. So it's how much the graph rises or falls vertically divided by how far to the right the line extends. Now let's talk about consequences of this way of defining slope. So let's look at this first bullet here. Now if delta y is large relative to delta x, so in other words this distance here is much larger than this distance, the value of m will be large. So if this number is large relative to this, it means this whole thing is going to be a fairly large number, and the line or the line segment should be steep. Let's draw a picture of this. So if I drew a line that had those characteristics, it would look something like this. It would be fairly steep. And the way you can tell is if I draw 2 points, you can see that the change in x is small, but the change in y is much bigger. So in a case like this where the change in y is big and the change in x is pretty small, you're going to have a steep line, and it's going to result in a large m value. Now, on the other hand, suppose delta x was large relative to delta y. So in other words, this distance is much larger than this distance. Well, if this delta x is much larger than delta y, it's going to mean that this fraction is pretty small, closer to 0 in other words. So the line, the m value is going to be small. And what will the line look like? Well, I'll draw a picture of that. So imagine I had a pretty shallow line like this. So I'm going to mark off 2 points on this line, and I'll make a triangle there. So notice here that the delta x is large and the delta y is small. So the line moves to the right quite a ways before you can see it going up much at all. So the line is very shallow, and in terms of the m value, the delta x is very large, the delta y is very small. It means this number is going to be pretty small, so m is going to be small. So bottom line, if you have a very shallow line, m is going to be small. If you have a very steep line, m is going to be quite large. Now let's look at the second bullet. In the picture above, we could see that delta x is positive. That's because delta x is calculated by taking x2 minus x1, and you can see from the graph that x2 is larger than x1. So delta x is a positive quantity. When delta y is positive, as it is in the graph, again, delta y is calculated by taking y2 minus y1, and in the graph, y2 is larger than y1, so delta y is positive. So when delta y is positive and delta x are positive, the line or the line segment will be increasing. In other words, the line is going to have an upward trend like this. As you go from left to right, the line has an upward trend. However, if delta x is positive, meaning you're going to the right, x is increasing in other words, but delta y is less than 0, which means y is decreasing, that means the line itself will be decreasing. So let's draw a picture of this. So I'm going to mark a different point down here. So for a moment, ignore this point. Forget that we had that point. I'm going to mark a new location for x2, y2. Maybe it's right here. So let's imagine this is x2, y2 right here, and I'm going to make a new line segment connecting them. So notice that delta x is the same. This interval here is exactly the same as it was before, but y2 is much less now than it was previously, and in fact y2 appears to be maybe about right here. So when I calculate delta y, and again delta y is equal to y2 minus y1, notice I'm taking a smaller number and subtracting a larger number. My ending value for y is less than my starting value for y. So my delta y, my change in y, will be negative. So when delta x is positive, but delta y is negative, in other words, y is decreasing, the line will be decreasing. And that's what you're seeing in this line. It has a downward trend as you move left, right. In general, when m is positive, that would correspond to delta x and delta y both being positive, meaning both x and y are increasing. Then you're going to have an increasing line, like this. It will have an upward trend. But when m is negative, that generally corresponds to delta y being negative. In other words, y is decreasing. you're going to have a line that is decreasing. In other words, it'll have this downward trend. Let's try out these ideas in the next example. On the axes provided, draw 4 lines passing through the point 0,5 with the slopes indicated below. Well, first of all, let's make sure we know how to interpret the slope here. If we look at this graph, notice that on the horizontal axis we have the letter y. That means, first of all, that y is playing the role of the input. And on the vertical axis we have r. That means r is our output variable. Now, you'll recall that slope, or m, is the ratio of the change in the output to the change in our input. So in this case, that would be the change in r divided by the change in y. Okay, let's look at part A. In part A, the slope is a half. So in other words, we're saying that the ratio of the change in r to the change in y is 1/2. You can think of the 2 as representing a change in y and the 1 as representing a change in the r. So we are changing y by 2, we are changing r by 1. Now, a change of 2 means we've increased. We've increased by 2. So what we're saying here is that when we increase y by 2 units, we also increase r by 1 unit. So let's see how that plays out. If we start from the point 0,5, which is right here, and I increase my y coordinate by 2 units, that means I go out here 2 units, I'm obligated to increase r by 1. That would move me up here. So I get another point. Let's do it again. If I increase y by 1, I'm obligated to increase I increase y by 2, and I'm obligated to increase r by 1. So if I keep doing that, I get a series of points. And these points, if I connect them with a line segment, the line segment looks like this. So this line that I've just drawn has a slope of 1/2. Now let's look at B. In the case of B, the slope is -2/3. So -2/3. That's our change in r over our change in y. So in this case, the change in y is 3, and the change in r is a -2. So for this line, here I'm going to put a line here to separate those. So for this line here, every time we increase y by 3 units, we have to decrease. How do I know decrease? It's because this change is negative. Anytime a change is negative, you have a decrease. Anytime we increase y by 3 units, we have to decrease r by 2. So let's see how that plays out. So if I start again from the point 0,5 and I increase y by 3 units. So let's see, I'm going to do this in a different color. So I'm starting from here and I increase y by 3 units. I'm obligated to decrease r by 2, so I go down 2, and that puts me right there. If I connect these 2 points with a line, then that is the line that has a slope of -2/3. You can see that this line has a downward trend. It has a downward trend because its slope was negative. This line had an upward trend because its slope was positive. Now let's look at part C. In part C, the slope is -1. The first thing I'm going to do is I'm going to take this -1 and I'm going to rewrite it as a fraction. We can rewrite it as -1/1. So this is our change in r over change in y. So we can see here that the change in y is 1 and the change in r is -1. What this tells me is that whenever y increases by 1, r has to drop by 1 unit. So let's see how that plays out on the graph. I'll use black for this one. Again, if I start at the same point and I increase y by 1 unit, r has to drop by 1 unit, and so that puts me right here. I can continue doing that if I wish. I increase y by 1, decrease r by 1. If I connect these points with a line, I get this line. This line has a slope of -1, and again you can see the line has a decreasing trend, and that corresponds to the fact that the slope is negative. Now let's look at D. The slope is 2, so I'm going to take my 2 and I'm going to write it as a fraction, 2/1. So this is our change in r over change in y. So the change in y here is 1 and the change in r is 2. This tells me that whenever I increase y by 1 unit, I have to increase r by 2 units. So let's go ahead and try that out. I guess I will use red for this. So again, I start at 0.5, and if I go and I increase y by 1 unit, I have to increase r by 2. So I go over 1 and up 2, and that brings me to this point. I could do this again. Increase y by 1, increase r by 2, and that gives me another line when I connect the dots. This line has a slope of 2. So one thing that's worth just looking at here, if you ranked these lines in order of smallest m to biggest m, 2 is the biggest slope, and notice that the steepest line is this one. So the biggest slope corresponds to the steepest line. The most negative slope is the -1 right here, and that corresponded to the black line, which was also a fairly steep line, but in a downward direction. In this next example, we explore the relationship between average rate of change and slope. The graph in this picture shows fertility rates in the United States between 1908 and 2010. A fertility rate is the average number of children a woman has in her lifetime. So that's what we're looking at in this picture. So, for example, if we just look at this point right here, what it's saying to us is in the year 1910, the average number of children a woman had is about 3.6. So that's how to interpret this graph. You can see that time is on the horizontal axis, so that's our independent variable. And we have the fertility showing up on our vertical axis, so that's our dependent variable. And we're going to use this graph to answer some questions. So let's go ahead and look at Part A. Estimate the average rate of change in fertility during the period from 1954 to 1974. And then we'll explain in practical terms what this rate is saying about how fertility rates have changed over this time period. So when we've calculated average rates of change in the past, we've always started with a table of values. So we'll begin there. To get our table of values, we're going to need to look at the graph. So I'm going to pull it back down here. We are interested in what's happening in the period from 1954 to 1974. So let's look at the year 1954 first. 1954 would be approximately right here. And if I go from 1954 up to the graph, it hits the graph approximately that point. And then from that point, I can go over and I can get an estimate for the fertility in the year 1954. If I eyeball it from my graph, it appears that the fertility, it might be 3.5 or 3.6. Maybe, let's just say it's 3.6. Now let's look in the year 1974. The year 1974 would be about here. And if I start from there and I go up to the graph, I arrive at a point. I'll mark that point. And then I start from that point and I can go over to get an estimated fertility in that year. And that appears to be around here. So this might be maybe about, say, 1.8 children per woman in the year 1974. So now that we've got some information from our graph, let's make a table of values. So we've got the year and we've got fertility. So remember, this is our input and this is our output. So in the year 1954, the estimated fertility was about 3.6 children per woman, and in the year 1974, the estimated fertility was about 1.8 children per woman. Now let's go and calculate the average rate of change in fertility during this time period. Recall that the average rate of change is calculated by taking the change in the output, and dividing by the change in the input. So for us, that's the change in the fertility divided by the change in the years. Okay, the change in the years. We take our ending value, subtract our starting value. That's 20. So we have 20 years. And the change in fertility, again, we take our ending value, subtract our starting value. 1.8 minus 3.6 gives us a negative 1.8 children per woman. So if we work this out on our calculator, we find we get negative 0.09. I'm going to put this over a 1. Children per woman per year, per 1 year. So now let's explain in practical terms what this is actually saying. The denominator represents the change in years. So we're saying with each additional year, we increase the years by 1. So with each additional year, the fertility decreases. We know it decreases because it's negative. The fertility decreases by an average of 0.09 children per woman over this time period. So let's go ahead and write that out. So each year between 1954 and 1974, the fertility decreased by an average of 0.09 children per woman. Okay, let's move on to Part B. The average rate of change that you estimated in Part A is actually the slope of a line segment that connects 2 points on the graph. Let's go ahead and draw this particular line segment. Well, if we look at our graph, we were calculating the average rate of change over this time period here, and in order to do this, we used these 2 points on the graph. If I connect these 2 points on the graph with a straight line, which I can do, the slope of that line would be calculated in exactly the same way as I calculated the average rate of change. So a very important point needs to be understood here. This formula, change in output over change in input, calculates both the average rate of change and the slope. They are exactly the same thing. So the negative 0.09 that we calculated, that is actually the slope of this line right here. It's both the rate of change of fertility over this period, it's also the slope of this line segment. Now let's look at Part C. Which of the following average rates of change would be larger? Over the period from 1934 to 1954, or over the period from 1974 to 2010? And explain your answer. Well, to answer this question, we can use what we've just learned. We can think of average rates of change as slopes of line segments. So let's go ahead and draw these 2 line segments, and then we'll compare their slope values. Let's start by looking at the period from 1934 to 1954. Now, over that time period, we have 2 points on the graph that we can look at. So let's see, 1934 is about here, and 1954, we already have that marked. So we have 1934 and 1954 marked. And if I start at 1934 and I go up to the graph and I mark that point, it's right around there. Then what I can do is I can make a line segment that connects my 1934 point with my 1954 point. So that line segment looks like this. So this is the line segment for 1934 to 1954. Now let's look at the period from 1974 to 2010. Well, we've already got our point for 1974. That's right here. Now let's look in the year 2010. That's over here. If we look at the graph, we have a point right here. And if we connect these 2 points, the 1974 point with the 2010 point, if we connect them with a line segment, we get this line right here. So, the average rate of change of fertility over the period from 1934 to 1954, that's the same as the slope of this line. and the average rate of change of fertility over the period from 1974 to 2010, that's the slope of this line. So if we want to know over which period is the average rate of change greater, we have to ask, well, which of these lines has the bigger slope? Clearly this does because it's steeper. So therefore, the average rate of change over the period 1934 to 1954 is larger. So we would write 1934 to 1954. That's the larger one. We end this screencast with a summary. So suppose that x1, y1 and x2, y2 are two particular input-output pairs of a function. And let's suppose that x1 is smaller than x2. Then the average rate of change of the output y with respect to the input x over this interval is the same as the slope of the line segment that connects these 2 points. So again, if you're using these 2 points to calculate an average rate of change, then that average rate of change is exactly the same thing as the slope of the line segment that contains these points. The average rate of change, we've written this before, is the change in the output divided by the change in the input. The change in the output is always calculated by taking your ending value minus your starting value. Again, ending value minus starting value for the change in x also. And this is precisely the same thing as calculating the slope of the line segment that connects the 2 points x1, y1 and x2, y2.